Now we have a combined talk again from Na'ama and Valeriya, and joint title is Characterizing the Galactic Double White Dwarf Population. And Na'ama will start with observations. And then Valeriya will take over, and we have 10 minutes questions after this combined talk.
Thanks. In the next 20 minutes, me and Valeriya will tell you a bit about characterizing the galactic double white dwarf population. In the first part, I will tell you about what we learned from observations and what are the implications it has for the type 1a supernova progenitor problem. This is based on work I've been doing together with Dan Maoz and Carlos Badenas. And then Valeriya will tell you more about the implication it has for the future LISA observation. And this is a work we are doing together with Sylvia Tonen. Okay, so why should we care about double white dwarfs? First of all, you should care about them if you're interested in binary evolution, or in type 1a supernova progenitors, or as gravitational wave sources. Now, Valeriya will focus on the implications for the gravitational wave space mission LISA, and in my talk, I'm going to talk about the implication for the type 1a supernova progenitors. So, why should we care about type 1a supernovae? Type 1a supernovae are important because they are a major source of heavy elements, and people have used them as standard candles in order to estimate distances, and this is how dark energy and the accelerated expansion of the universe were discovered. However, nobody knows exactly what is exploding and how, and this is the so-called type 1a supernova progenitor problem. So, the leading scenario, or one of the leading scenarios for type 1a supernovae in the recent years has been the double degenerate scenario, in which we have a binary consisting of two white dwarfs. They lose energy and angular momentum to gravitational waves, spiral in, merge, and possibly explode in a 1A explosion. Now, if this is the leading scenario, if this scenario is correct, there should be enough closed double white dwarf system in order to reproduce the observed type 1a rate in the Milky Way. So we want to look for double white dwarfs. An efficient way to do it will be to look for radial velocity variations in white dwarf spectra. We take a large spectroscopic sample of white dwarfs, where each white dwarf has more than one epoch, and we look for radial velocity variation. And this is what Carlos Badenas and Dan Maoz have done back in 2012 with the SDSS. They took a large spectroscopic sample of about 4,000 white dwarfs, and they measured the delta RVmax distribution, where delta RVmax is the maximal observed radial velocity difference per system. And this is what they got. Here in black, you can see the observed delta RVmax distribution. And you can see that this distribution has a very wide core, up to 250 kilometers per second. Now, systems that fall in the core of the distribution are either binaries or single white dwarfs with just large measurement errors. So we can't say a lot about systems that are in the core of the distribution. However, systems that are in the tail of the distribution are very likely to be real double white dwarfs. And then we can follow them up and orbitally solve them. What they wanted to do next is to compare this observed delta RVmax distribution to a simulated one. And for that, we need to simulate the local double white dwarf population. Now, how do we do it? First, we need to draw the primary mass, which we do based on the observed white dwarf mass distribution. Then we need to decide whether it's in a binary or not, which we do based on a parameter we call F-bin, which is the fraction of all white dwarfs in binary up to a specific separation to which our data is sensitive to. And in the case of the SDSS, this is 0.05 AU. Now, if it is a binary, we need to assign it with a secondary mass, which we do based on a power law with an index beta. Then we need to assign it with a separation, which again is drawn from another power law with an index alpha, which is the separation distribution of double white dwarfs at birth, after the last common envelope phase. Now, from here on, we know exactly how this system is going to evolve. It's just going to shrink and emit gravitational waves. And so after 10 gigayears of evolution, we'll have a shorter orbit. And we go on and assign it an inclination drawn from a sin-I distribution. And finally, we get the theoretical RV curve for this specific system. We go on and sample this theoretical curve based on a sampling sequence drawn from the actual observed sample. We assign it a measurement error. And finally, we get the delta RVmax of this specific simulated system. We go on and repeat the procedure for many other simulated systems. And then we get the theoretical delta RVmax distribution for this set of parameters. And here you can see in black again the observed delta RVmax distribution for the SPSS sample. And the colored lines are the simulated distributions for different combinations of the parameters. Now, it turns out that the parameters that govern the shape of this distribution are FBin, which again is the fraction of all white dwarfs in binary within a specific separation, and alpha, which is the index of the power law of the separation distribution of double white dwarfs at birth. And Badens and Maoz have done it for many combinations of alpha and FBin, and they got this 1 and 2 sigma contours that you can see here. And the solid lines that you see are of constant merger rate. And what they discovered is that the double white dwarf merger rate is very similar to the observed type 1a rate in the Milky Way. However, because of the large measurement errors of the SPSS, this was very uncertain. So we needed a better sample with more precise measurements. Luckily, such a sample exists. The SPY sample, or the ESO-VLT supernova 1a progenitor survey, was a large program that was carried out about 20 years ago already by Napivotsky et al. With UVs from the VLT. They got high resolution, high signal to noise, multi-epoch spectra for about 800 white dwarfs. And here you can see an example for a spectrum of one of these white dwarfs from SPY. And because of the high resolution of UVs, when we focus on the H-alpha line, for example, we can use its narrow NLTE core in order to get a resolution of about 1 kilometer per second compared to the 80 kilometer per second Karas and Dani got from SPY. So we're from SPSS, sorry. So we repeated the same experiment, but for the SPY sample, which is smaller. We have only 400 white dwarfs compared to the 4,000 of the SPSS. And we got this delta RVmax distribution. And if you compare it to the one from the SPSS, you can see that this time the core of the distribution is much narrower. It goes only up to 10 kilometers per second compared to 250 kilometers per second. And we have this very long tail of double white dwarf candidates. So these two samples, SPSS and SPY, actually complement each other. So what we did next is to combine the results we got from both samples. And here you can see the 1 and 2 sigma contours in blue from the SPSS sample, in green from SPY, and red is the combined contours. And the solid lines are of constant white dwarf merger rate. And what you can see is that the white dwarf merger rate is much higher than the type 1a rate in the Milky Way. Now, if we focus on the combined contours, what we see is that about 10% of the white dwarfs are double white dwarfs with separation up to 4 AU, and that the white dwarf merger rate is about 6 times higher than the specific type 1a rate in the Milky Way. Now, I should note that this is completely consistent with the 6% binary fraction from the SPY sample of Napivotsky et al. When we considered only separations up to 0.1 AU as they did, while the 10% is for the 4 AU separation range. So what does it mean? If we multiply the white dwarf merger rate by the galaxy lifetime, we get that about 10% of the white dwarfs have already merged with other white dwarfs. And if we consider that the type 1a rate is 6 times lower than the white dwarf merger rate, then we get that about 15% of double white dwarf merger must lead to a type 1a supernova explosion if we assume that this is the main channel to type 1a explosion, and that about 10% of the white dwarfs that we see today are merger products of white dwarf mergers that didn't explode as 1a. What next? We got a lot of time with UVIS on the VLT to follow up all those double white dwarf candidates from the tail of the distribution. And with the help of many other collaborators, we got also time on the GTC, LBT, and so also following up those candidates and those from the SDSS. And then we will be able to solve, to get the full orbital solution for this system, or actually throw them away. And then we'll be able to say more precise things about the population. And SDSS-5 that has started recently will get multi-epoch spectra for 100,000 Gaia white dwarfs. So there is much more to wait for. And with this, I'll leave you with Valeriya. Thanks.
First, I will unmute and then share the screen. Share, present. Just a sec. Oops. I wanted to get my pointer. So can you see my presentation now?
Yes, very well.
Can you? Okay. So in this part of the talk, I will show you the future prospects for double white dwarfs with LISA in 2030s. And I would like to start by giving you the motivation why LISA will be important for double white dwarf studies. So as you all know, electromagnetic radiation from white dwarfs is faint, and it does not allow us to observe them beyond a couple of kiloparsecs. So LISA will be a revolutionary instrument for breaking this limit, because with LISA we will see white dwarfs in double white dwarf binaries much farther away, potentially reaching 1 megaparsec. And of course, with the big, larger volumes will come higher detection numbers. So in this plot, I'm showing you LISA frequency coverage on the x-axis versus gravitational wave strain. That is basically the amplitude of gravitational waves. So the black dashed line here shows LISA sensitivity curve, while the other lines and colors represents the variety of LISA sources. So the blue points right in the middle of the LISA band are our galactic double white dwarfs with period of at most a couple of hours. And the number of blue points on this plot completely outweighed the number of other LISA sources, even combined all together, to the point that at the lowest frequencies, so below millihertz, double white dwarf signal starts to blend and form this confusion limited background for the LISA emission that you see in a gray shaded area. So the result binaries, the blue points will appear as monochromatic gravitational wave sources with the small and slowly evolving drift in frequency, and they will emit continuously over the whole duration of the LISA emission. And such a signal can be encoded in with 8 parameters that I'm listing here on the slide. So the last 5 of which are angular parameters, such as chi position, inclination, and so on. And I'm not going to touch them because I can average over them when I compute LISA response. So I will then go on. We have gravitational wave frequency that is equals twice binary orbital frequency, because gravitational wave radiation is quadrupolar. We have the frequency drift that we call chirp, that is governed by this parameter m that we call chirp mass, and is basically a combination of white dwarf component masses. And finally, we have the amplitude that primarily depends on the frequency, then the chirp mass, and the distance to the binary. So we can now employ exact same model as Na'ama just nicely showed to us to sample white dwarf masses and frequencies to see what are the implications for the LISA rates. So I'm not going to repeat the details, and I'm showing you here only the results that I get. So from the left to right, you see the distributions of the primary, secondary, and the chirp mass on the left. Then I have the distribution of orbital separations for double white dwarfs that are considered within the maximum allowed separation in the LISA band that I translate into gravitational wave frequencies. And then in addition to that, we also have to sample double white dwarf positions. And that I can do by choosing a density distribution for the Milky Way. And for now, I'm considering disk only. And here I'm considering a profile that has an exponential radial dependency and isothermal vertical dependency. So finally, the last piece is to compute how many binaries do I need to sample. And then I can do by first taking the volume that I'm simulating, and that is given by the integral of my density distribution. Then I need to choose a white dwarf density. And here, for instance, I'm using the value derived on the 20 parsec sample by Mark Hollands. And then we have the binary fraction derived by Na'ama and collaborators that I need to rescale to the LISA frequency band. So by multiplying these three numbers, I get around 4.5 million white dwarfs to model. So now we have all that is required to compute the signal to noise that these binaries will produce in LISA, because we have the amplitude, we know the LISA angular response, the mission lifetime, and the SN on this slide, that is the noise response of LISA with frequency. So what I found is that I found 28,000 binaries above the signal to noise threshold to considered as detected. And I'm showing these binaries on the right, again in the frequency characteristic strain plot. And as a comparison, here you see some orange stars that are currently known double white dwarf binaries. So now we can check how whether this estimate is robust, and for that we perform some variations of the model. So, for example, we considered the most extreme values of power law index alpha that Na'ama explained to us, and the double white dwarf fraction within this 1 sigma contour that Na'ama and collaborators derived based on the SDSS and the SPI samples. So for the lowest possible values I'm showing here, we have actually an increase of 31% in LISA detections. This is compared to the default value that is using best fit parameters. And for the highest possible values of alpha and double white dwarf fraction, we have a decrease in 21%. And this is the largest variations that we came up with. And we also did some modifications to the distribution of the primary and the secondary white dwarf masses, and these are shown here in the middle, all of which have a moderate effect on the LISA detections of at most 13%. And this tells us that our estimate is robust. And if we now want to compare this number with the estimates based on the binary population synthesis models, the main message that I want to deliver here is that I get twice as many binaries, twice as many LISA detections based, for instance, compared to, for instance, my own earlier estimates. And this is mainly because here in the middle, I'm showing you that we have a bit more high frequency binaries, and also the chirp mass distribution are now peaking towards higher value, and both of these quantities go to increase my amplitude and the signal to noise ratio, so I get more detections. So now what will we learn from the LISA sample? So of course we can.
We're running a bit of bit late. We're running a bit late. If you can
Yes,
be
I
quick.
will. I will conclude now. So besides, using this large sample to study the population and the evolution of these binaries, we can use them as galactic tracers because they are numerous. And on the left, you can see that they are widespread and we can really see them everywhere in the galaxy. So just by looking at the spatial distribution and looking at the density profiles of the LISA detections, we can recover the bulge, the disk, and the disk scale radii and the disk scale height. And we can also characterize the shape of the bar, as you can see on this plot. So we can derive the bar's length, axis ratio, and orientation. And we estimate these measurements to be competitive with those based on optical and near-infrared tracers. And my really final slide that I want to show you is that we can even go beyond our galaxy to study double white dwarfs. So here you see the density of LISA detections in the galaxy in red and yellow colors. And the blue stars and points are Milky Way satellites. So we found that we can actually see some of the satellites, those that are more massive than 10 to the 6 solar masses, to shine, in gravitational waves. And of course, those that are the most massive, like the Magellanic Clouds, we can actually spatially resolve in gravitational waves. We can then use LISA detections to weigh the satellites. In a similar way, we use the total stellar light to estimate the mass of the galaxy. And we can also potentially discover new satellites in this way. For instance, looking at the regions of the sky that are inaccessible to optical surveys, such as behind the bulge or the bar. And with that, I hope that I convinced you that LISA really will open a full landscape of the local group for double white dwarf studies. And we will now take your questions.
Thank you very much for these two nice talks. We have time for some questions, of course.
Yes.
Tom was first.
Yes, thank you for that talk, Valeriya. The SPY double white dwarfs are very skewed towards low mass white dwarfs, at least the visible white dwarf. Do you account for the mass distribution in your models, that it's rather biased towards low masses, or
Yeah, actually, are you referring to the LISA estimates, or? Yeah.
Yes, yeah. So your numbers are 48,000.
Yes, so we did this the variations that are basically accounting for the mass of double white dwarfs that can be inferred from SPI, and yeah, the variation is not big. It's actually a bit more than 50,000. So it's less than 10%, but yeah. It is smaller than the variations due to the different power law of the double white dwarf distribution and the binary fraction.
Right, thank you.
Okay, next question, Carlos.
Oh, there we go. Yeah, that was really nice. I wanted to ask a question about the binary population synthesis calculations. We've found in sun-like stars in the Milky Way that the closed binary fraction is a very strong function of metallicity. Between solar metallicity and Fe over H of -1, the fraction of closed binaries goes up by a factor of 4. Right. Of course, double white dwarfs is very hard to measure the metallicity, but do you think that the metallicity or H of the progenitor systems could have an impact in this if the closed binary fraction changes by so much, right? That should have an impact on the binary population synthesis calculation results.
Yes. So we looked at this together with Sylvia Tonen. And maybe she can even comment more than me. But what we find is that Okay, so we looked at this problem as two separate problems. So one, of course, is the binary fraction, and the other one is the metallicity. And both have, in the models, have a very minor effect. So again, something like less than 10% when I look at the LISA rates. And that's because the metallicity affects the double white dwarf evolution in the binary population synthesis much less now compared to LIGO gravitational wave sources, so only at the later stages. And maybe Sylvia wants to add something.
Yeah,
yeah,
I'd love to, because yeah, as Valeriya said, there's two different effects. One of it is, you know, just how a star evolves differently at different metallicities. And that effect is not so big for the double white dwarfs. That's several tens of percent effect on the population. But then it's the point of not only the binding fraction being different at lower metallicity, but maybe also the period distribution peaking at more compact orbits. So for these, you know, relatively low mass stars, the majority of them have initial orbits where the stars don't interact and would never end up as a compact double white dwarf. So I think if you take this into account, so a higher binary fraction plus these initially more compact orbits, where we find more often mass transfer, then that could have an interesting effect on the population.
Thank you.
Xiao, last question.
Hi, thank you very much for the beautiful talks. So I have a question for Na'ama. Could you comment on how you deal with the selection effects of SDSS and also SPI? So like what Tom said, it seems the sample is not a volume limited sample. So then will that bias the result of like the merger rate or the fraction? I ask because I remember in the paper you said that if you use the combined result of SDSS and SPI, then it would predict all the high mass white dwarfs or ultra high mass white dwarfs are merger products. So that seemed to be too high. Sorry, we cannot hear you, Na'ama. At least me.
No, neither do I.
And now it's okay? Okay, sorry, I have problems here. So regarding the last comment, what we predict is that about 10% of the white dwarfs that we see today should be merger products, so they should be more massive. So 10% of the massive white dwarf, of the white dwarf should be like more massive. And regarding your question, yes, it's true that we have biases in our samples, in the SDSS and in SPI. They are less biased, for example, if we look at the ELM sample, which targets specifically low mass white dwarf, and therefore is going to almost always find white dwarfs in binaries. But now what we are doing is we do this follow-up. So okay, it still gives us the biases. We'll just have to do it again with a like less biased sample. But those were the least biased samples until very recently. Now with Gaia, we can do more. So maybe there is some reason of redoing it again with a well-defined sample from Gaia, volume limited. Yeah.
Thank you very much.
Okay. So no questions anymore. We are 2 minutes late, which is kind of good, I think. Thanks to all the speakers. Thanks for everybody who are participating in the questions. And now we have a break. See all of you in half an hour for the last session.